Hi, so hello, my name is Stephen Miller. I am a math professor at Williams College, and this is Calculus 2. If this is not the class you were thinking of, this is your chance to try to switch to the correct one. It's a little confusing at the start of the year because today is Friday, but yesterday was not Thursday, Wednesday was Thursday. So after that, it's going to be more standard in terms of how the days of the week go. So what I want to do today is get to know you all a little bit. I've changed plans a little bit. I'm assuming everybody has power. We actually lost power at our house for a couple of hours last night. I think all of campus is good, but just in case, I'm not sure if everybody's going to be able to make it to class. So I'm going to adjust things a little bit for the first week or so because we are still going to be remote until the end of, I think Friday next week is the last day we're remote, and then the Monday after that will be in person. So I'm going to be assigning homework, but I'm not going to have any of the homework due until the first Monday when we're in person. You are welcome to submit the homeworks either by email as a nice PDF or in person, whichever is more convenient for you. I obviously do not encourage you to wait until the last minute to do all the homework. There's going to be homework typically every day in the class, due at the next day, and the homework will be graded and gone back to you very quickly. So the idea is to get fast feedback as to what is going on. We are very fortunate that we have two strong TAs who are working with this class, and they're going to have office hours available throughout the week. Right now, we are staggering the office hours to be on Tuesdays, Thursdays, and Sundays, though there will also be some on Monday and Wednesday, just taking into account what the homework schedule is for students and when people start doing homework. If people really want homework sessions on Friday or Saturday, please let me know and we will adjust things accordingly. If I'm in my office, it's office hours, come by whenever, shoot me an email when you want to meet and chat. What I want to do today is talk a little bit about some of the motivation behind Calculus 2. Why are you taking this course? Some of it could be, well, I want to be pre-med and I know I need a year of college math, or at least that used to be the requirement. But I want you to see that there's a lot of really useful things that we can do in a class like this. And so in fact, what I'm going to do now is I'm going to share the link that I've sent you all earlier. So you should hopefully see right now a Google Sheet. And there's a question at the top. Do you plan on taking another math course after this? So put a 1 by the Math140 row if the answer is yes, absolutely. I know I'm going to take more math after this. Put it in the maybe column if you're not sure, and put in the no if you are, as of now, not planning on going beyond this. Obviously, if there's already a 3 in one of those spots, just increase it to 4. And I just want to get a rough sense of who is interested in doing various things. At some point later, I'm going to ask you to just, either come by my office, so we can chat, or go for a walk on campus, grab a coffee or a meal, so I can get to know you a little bit and try to get a sense of what do you want to get out of this. And that's related to the next question, which is, please list the topics you want to see, hopefully related to Calc 2 and Calc 3, but I'm always up for a challenge. One year when I was doing Math 150, somebody wanted to know about bees. And so I was quite happy to, try to work bees into the lecture. You are welcome to put your name in if you want. There's absolutely no need to do that if you don't want to. You don't have to do this now, you can do this later. But the more information I get from you, the more I can try to tailor the course to your interests. What are you doing in other classes? What might you be doing in the future? What might you be doing for the summer? How can we get you some useful skills? I used to tell all my students that if you knew 3 subjects, you would always have a job. You may not like it, but you'd have a job. And those were probability, statistics, and programming. One of the big applications of Calculus 2 is finding areas under curves. And it turns out that's related to calculating probabilities of events. I no longer make this promise because somebody sued her college when she did not get a job after graduation, discovering a new type of discrimination, academic discrimination. So she claimed her 2.7 was just as good as someone else's 3.7. So I can't promise you a job, but I have a huge number of contacts in the local business community who are always looking for strong students to do projects. Sometimes it's just to gain experience, sometimes it's actually paid. And so if any of you are interested in that, if you have some basic programming skills, you already have enough that there are some projects that you could work on. I also do a lot of work with students here on the mathematics of sports. I'm hoping to teach a class on that next year, where I've had students involved in a lot of lawsuits for Major League Baseball and other organizations. And again, for a lot of these, the material you'll learn in your first 2 years of college is already enough so that you can make some really good contributions. And so I already know Calculus 2. I've known Calculus 2 for longer than you've been alive. The goal is not for me to race through material. The goal is to try to cover the material in such a way that it's going to benefit with you in whatever you want to do after this class and after Williams. And that's why I really want feedback from you. Are you thinking of taking other math classes? What's your major? Come by, let's grab a coffee, let's go for a walk. Let me try to figure out how I can pitch this class to make it as enjoyable for you as possible. In some sense, I'm a little bit sad to be teaching this class. I have been a professor for over 2 decades, and I had never taught Calculus 2. I've taught Calculus 1 and Calculus 3 many times. And so I've been trying to go my whole career without ever teaching this class. And so, because of that, I don't actually have a huge amount of materials already prepared. And so what this means is both good and bad. It means I don't have a tremendous amount of resources to just throw you that are directly applicable to Calc 2, although I do somewhat because, since I teach Calc 3, I have all the handouts for Calc 2 that I need people to know. But it means that I have, no fixed material that I really want to do and cover, and that I'm really open to adjusting based on what you want to do. So it's a wonderful opportunity to take some control of your education. What do you really want to see? What really excites you? What do you want to use mathematics for? And there are so many different things you can use mathematics for. This is a chance to adjust. As I said, I haven't taught Calc 2 formally, but I am teaching Calculus 2 to some students at the local high school where I serve on the school committee. And so what I'm willing to do is I'm willing to make the following deal with you all. And you can think about this and email me later if you want to do this. If you watch the videos that I am making for my lectures with that Calc 2 class before class and come to class prepared, 60% of your grade will be a 92.5, which is right on the border of an AA minus. So I'll repeat that. So if you come to class prepared, having watched the material beforehand, 60% of your grade will be a 92.5, right on the border of an AA minus. What this means is if you do A work for everything else, you end up with an A. If you do a little bit below A work, you have a huge thing pulling you up. And the reason to do this is if you come to class prepared, if you come to class having already watched a 20-minute to 40-minute video, we can use class time a lot more effectively. We can figure out which parts were causing people trouble, and really focus on those. We can do more examples. The other thing, of course, is it frees up more time for applications. And it allows us to see what actually inspires people. Why do people actually care about material like this? So again, I will send details on all of this stuff later. Right now, this is just the standard mechanics stuff. I love to have class participation. And so after every class, if you make a comment, please send me an email about the comment that you made. It's okay if the comment is wrong. I do this for several reasons. One is a lot of times what you think might be a small minor comment is actually a really good observation. And two, a lot of times you find out that you need a letter of recommendation and you need someone to write for you quickly. The more detail I have from you, the better. And so if you send me a lot of these emails, I get to know you a little bit better. And if I have to write something, I can do something non-trivial. But perhaps the most important reason to do this is to get you comfortable in speaking up. So when I was an undergraduate, I was absolutely terrified to speak in class. And to some extent, I'm amazed that I became a professor because I could not speak in public. What changed it for me was when I was in graduate school, one of my friends told me that I should be a social chair in student government. And I was a little skeptical because I told her, well, a social chair is supposed to want to be with people, and that's just not me. And she knew it would be really good for me. So I said at dinner that night, if one of my friends will do it with me, I'll do it. And so one of my friends stood up and said, sure, I'll do it. And it was the best thing that happened. It really got me out of my shell. And so everyone here is smart, everyone here is talented, but what you want to make sure is that you get noticed. There's a lot of talented, smart people out there, and there's a lot of people who have really good ideas who just aren't seen. And I want you to get comfortable speaking up in public. It's hard. I know how hard it is, but the more you do it, especially when the stakes are low, the better it is. If you are afraid of saying something that's going to make you look foolish, we all have that. We all say things like that, but also almost surely people are going to be grateful when you are speaking up. My first year here, I taught a class on differential equations, and at the time we don't require linear algebra as a prerequisite, which makes the class very difficult when you want to study things such as your predator-prey systems. If you have rabbits and you have foxes eating the rabbits, how many foxes and rabbits will you have at a given time? So you have a system of two equations with two unknowns, the populations are functions of time, and these are differential equations and you want to solve it. And I asked the class, how many people want to see a review of 2x2 matrices? Because we don't need a huge amount from linear algebra, we need just a little bit. And so nobody raised their hand. So everybody's comfortable, nobody wants to see it. Okay, well, we had clickers back then. This is what you did before everyone had cell phones. And I said, I'm just curious. I'm not going to report the results to the class, but I'm curious. How many people want to see a review of 2x2 matrices? Press 1 for yes, press 2 for no. Now, I never said I wouldn't tell future classes. I only said I wouldn't tell that class. 43% wanted to see a review of 2x2 matrices. 0% felt comfortable speaking up in public. So almost surely, if there is something you want to see, if there's something that's not clear, odds are extremely high other people want to see it as well. And if not, the good news is it's going to help you get more comfortable speaking up in public, and that's one of the most valuable skills you can get. So in terms of mechanics, the way the class works is we will have, as I said, homework that is for the most part going to be due after each class at the start of the next class. Late homework will not be accepted unless some complete catastrophe happens immediately, unless you give me at least a day's notice. There should always be time to schedule things to let people know you want to get in the habit of getting things done on time. 60% of your grade will be adjusted to be a 92.5 if you want to opt in for that. 3 times all semester, you can email me before class and say, Professor Miller, something just happened and I just wasn't able to watch the material beforehand. And that's fine, as long as you email me beforehand. But if you opt in, I'm going to assume that you come to class prepared. If you have questions, if there are things that you want to see me cover in greater detail, just email me, or we'll have a Google Sheet where you can just put down, for today's lecture, please make sure you cover an example of partial fractions where the denominator is a quadratic. If anybody knows what partial fractions is when the denominator is a quadratic, you are in the wrong class. You should be in Calc 3. Talk to me afterwards. Okay, you should have no idea what that means right now. So there will be a couple of midterms. There will be no final. So every midterm but the last is one set. And unless you tell me otherwise, we just have somebody coming in. Unless you tell me otherwise, I will drop one of your first 2, 3, or 4 midterms. The last midterm must be kept, and that one will count, I believe, 40%. All the other midterms will count 40%. Homework will be 15%, and class participation will be 5%. You do not lose points for saying wrong answers when you speak. So again, unless you tell me otherwise, I will drop your lowest midterm. And one of the reasons to do this is, for some of you, it may be many years since you've done a calculus class, and it is a jarring experience when you first come. So I have, practice problems and practice exams that if you want to, you are absolutely welcome to look at. I strongly encourage you to work in groups. When you are working on things and you hand in homework, just write down, I worked with so-and-so, and just mention who your group is. And the goal is at the end of the semester, to get to the point where you understand the material. If you are having trouble in the beginning of the semester and everything is clicking by the end, I'm happy to wait the earlier exams a little bit less and the later exams a little bit more. The last, and then I'll see if there's any questions, is if you want to do a project, I am happy to adjust your grade, and 10% of your grade can be doing a project where you apply mathematics. It doesn't have to be directly related to Calculus 2. It's nice if it is, but just to try to see how do you apply mathematics in the real world, extremely useful. And this could, of course, be a great way to practice some coding. Your coding is a wonderful, wonderful skill to have. And we will talk a little bit over the course of the semester how to use the various online resources to do things. When we get back to the point when we can see each other, I might bring down some of the old tables that I have for my office. I am old enough that when I was in high school, they taught us how to find logarithms and values of trig functions by using tables and interpolating. We did have calculators, but that was a skill that was still taught. That skill is no longer taught. We were taught a lot of skills on how to sketch curves. If anybody wants to put in the chat, if they were taught how to do curve sketching when they were in high school, or if you took 130 here, if that was something that was covered, that would be interesting to see. The topics change a little bit over time. The fundamentals of calculus doesn't change. This has been pretty stable for centuries now. But as we have more and more resources available, what we spend time forcing you to learn or teaching you to do is very different because so much can be done now. If you've taken any stats classes, in the old days, you would actually have to calculate a lot of the sums to calculate standard deviations or means by hand. And now with one line of code, it just takes your data and it just spits that out. All right, so I'm going to stop here and see if anybody has any questions on anything that has happened to date. Okay, I see something in the chat. Okay.
I have a quick question.
Yes.
Will all this information be on like a syllabus anytime? I know there's one on the website, but I'm just not sure if you'll send another one.
No, I mean, basically what I have on the website is very similar to what I've just said now.
Okay.
And there should be a Math 140 introduction.
Okay, thank you.
Yep. And again, if you ever have any questions about what is going on for the class, just let me know. For the most part, I don't use Glow. I host things off of my homepage at Williams. The advantage of this is you do not have to be logged on to Glow to have access to it. Once you leave Williams, you still have access to any of the materials and handouts there. Right. Any other questions or comments about the mechanics of the course? Okay, so what I'm going to do, yes.
For the part where you mentioned we could get 92% for 60% of our grade if we come prepared, how exactly does that happen? Do we do a test every day? We come
Nope.
to class,
So I will be sending you video links and you are on the honor code to watch the video before class. So 3 times all semester, you can email me before class starts and say, I didn't have time today to watch the video. I understand things can happen. Now, of course, you can sometimes watch some videos ahead of time. And so if you happen to have a week where you don't have that much work, it's a great opportunity to put a little bit of stuff in the bank. So my feeling is I would like to trust students. I don't want to have to put in quizzes and more work for you to make sure that you are doing things. This is a school where we have an honor code where we trust you. So if you agree to do this, then I will assume that you are watching the videos. And if you haven't watched the videos, you will let me know. I'm not going to give you a quiz for each class. But when you watch the videos, it's going to be far more effective for the lecture that follows. If there's something that is unclear to you, if there's something that you want us to cover in greater detail, if you then just put a note to that on. So thank you for the questions. Any other questions or comments on the mechanics?
In terms of kind of choosing that option, should we just, I guess you said shoot you an email in the next few days saying you want to do it?
What I'm going to do is I'm going to assume everyone has chosen the option. So I'm going to do it as an opt-out.
Gotcha. Okay. Thank you.
So I'm going to assume that everybody likes the idea of having 60% of their grade essentially an A. And so if you don't want that, let me know. It's very similar to, I'm going to assume everybody wants me to drop their lowest midterm score of the first few, unless you tell me otherwise. I actually have been at schools where people have not wanted their lowest midterm score dropped. Extra credit if anybody can think why.
Is it for like accountability reasons? Where they
In
just
what
want
way?
consistency?
I'm sorry?
Do they want it because of consistency and accountability?
No, they wanted to lower their average.
Oh.
So the reason is I was at a school where if you get an F, it doesn't show up on your transcript. And so there were some students who would rather have an F and the class not show up on their transcript than a C and have it show up on their transcript. And so there actually was an incentive to fail a class rather than getting a C. The point of this is you always have to think, when you're putting something in place, what kind of behaviors are you encouraging, and are these the behaviors you want to? Is anybody here familiar with the women's badminton scandal from the Olympics a couple of cycles ago? So people had actually warned that something like this could happen before it happened. And the way it was set up is, I believe it was one of the Chinese teams noticed that if they won their game, they would have to play another Chinese team in the next round. But if they lost, they could avoid playing a team from their country. So they deliberately threw their match, and they did it in a very non-subtle way, hitting the birdie directly into the net, deliberately missing. And once the Chinese team deliberately lost, then I think 3 other teams deliberately lost. And so they all had enough points to move on to the next round, but they were deliberately losing to affect their seeding as to whom they would play. And in the end, the teams were all disqualified. Although what they did was legal, unless you start looking at good sportsmanship rules. Are there implicit contracts that you are going to try your hardest? You can imagine how excited the fans were to watch a game that they had paid good money for, where people are deliberately missing or hitting the birdie into the net. And so you always want to think about, what are you encouraging? If you are not going to be taking more math classes after this, the amount of the material in Calc 2 that you're going to use for the rest of your life, and I know this is being recorded, is minimal. Most of you, if you don't continue in mathematics or related allied science, are probably not going to be calculating integrals and finding areas. So because of that, what do I want you to get out of a class like this? I want you to get out of this class how to think about material, how to learn, how to see what's out there, how to solve problems, how to think about things, how to try to build some intuition. Those are skills that are going to serve you tremendously. This is one of the reasons why, if you want to do a project, I'm a strong supporter of a project, because you will learn a lot of valuable skills in terms of how to write something up well, how to present. It doesn't matter if you are correct. If you can't convince the people who say yay or nay, it doesn't matter how good your analysis is. So if there is something that excites you and is somewhat related to mathematics, always happy to talk with you about turning something like that into a project. Any other mechanics questions?
I just have a question about the videos and recorded lectures.
Yep.
So do you post those on your
So I will be posting the our class videos on my homepage, on the Math140 homepage, which you all have a link to. And every day after class, I will send you an email. Here is the video. It's now been uploaded. So today's video will be uploaded sometime later today. I'm teaching 150 immediately after that, and then I'm teaching the high school kids immediately after that. So it may be a while before I upload things, but they will be uploaded, later that day.
Okay, thank you.
Yep. Any other mechanics questions? Okay, so the last item before we move into content is letters of recommendation. So every now and then I get an email from somebody I taught maybe 10, 15, sometimes even 20 years ago, saying that they need a letter of recommendation. And for some people, it's absolutely no problem. I remember them very well. For others, it's much harder, and they never really got to know any of their professors in college. And so one of the things I urge everyone to do is each semester, you should choose as a goal getting to know one professor well enough that they can write a letter of recommendation for you, and that they know you so that if they see an opportunity that you would be good for, they can pass it your way. I am happy to be that person. I'm happy not to be that person. If you try every semester and you succeed half the time, by the time you graduate, you'll have 3 or 4 professors who know you well enough who can write letters for you. And again, this is extremely valuable. You don't know how life is going to turn out. If you think you might need a letter of recommendation from someone, a good time to ask them is when the class ends and say, hey, professor, I really enjoyed your class. I might be applying for some things, for some summer internships next year. Would you be willing to write a strong letter of recommendation for me? And then that way they can actually write a letter while everything is still fresh. All right, so I want to talk a little bit about, why do we care about Calculus 2? So to some extent, you must care a little bit because you took Calculus 1 and you're still here and you're going back for more. So why did we do Calculus 1? Well, Calculus 1 is mostly about the derivative, and then depending on where you go, you do some integration. And so it's much better to do this in class when I can just quickly look at everybody and just get a sense of who's seen what. But later in the semester, I'll get a sense of how much integration has everyone done, as well as how rigorously has everyone done things. It is very easy in mathematics to give arguments that look reasonable, but are actually flawed. And so later in the semester, I might give you a few examples of this just to highlight how careful you have to be when you're doing mathematics. And so Calc 1 is about the derivative, about how things change with time. So if you have some curve, f of x, which is distance, then the derivative tells you how quickly things are changing. So Calc 2 is about integration. It's the other direction. If I give you a function, what's the area under the curve? So if I give you a function, we're trying to find the antiderivative, also known as the integral. So why do we care about areas under curves? Well, one of the biggest applications is probability. So can somebody give me, when you hear probability, what do you think of when you hear probability?
I think of a fraction or a percentage.
Good, fractions or percentages. So -3/18. Is that a possible fraction that I could think of for probability?
I would say it's possible as a fraction, but after hearing area under a curve, I don't know if you can have a negative area. Can you?
Well, could you have a negative probability for something?
No.
No, no matter how bad you are, your probability of winning can't be below 0%. And similarly, your probability of winning can't be above 100. So probabilities have to be between 0 and 1. So if we have discrete events, the 2 big examples people use is, tossing a coin or rolling a die. And in both of these, you can calculate, what's the probability of a head, what's the probability of a tail. If the coin is fair, we would say 50% of the time or 0.5 we get a head, 0.5 of the time we get a tail. If you have a fair die, you get each of the numbers 1 through 6 with probability 1/6. And then you can start to consider more interesting examples. What if I roll 2 fair die? What are the possible outcomes when I roll 2 fair die? So if I roll 2 fair die, what are the possible outcomes for the sum? So what are the possible values for the sum if I roll 2 fair die?
Any
You
number
get-
between 2 and 12.
Any number between 2 and 12. And now we have to put on our English hats. When you say between, do you include the endpoints or not?
Including
Yeah,
2
so
and
I would
12.
say any number from any integer from 2 to 12. So it could be 2, 3, all the way to 12. Do you think all of these outcomes are equally likely?
No.
No. So which outcomes do you think are very unlikely?
2 and 12, the
Yeah,
ones
2
on
and
the
12.
edges.
Yeah, and in fact, so the probability of a 2 equals the probability of a 12 equals 2 out of 36. The probability of a 7 equals 6 out of 36. And it turns out it goes linearly. The probability of a 3 is the probability of an 11. And so for, oh, I'm sorry, it's not 2 36s. Sorry, it's 1 36. This is going to be 2 36s. Because for a 3, we could get a 2 and a 1 or a 1 and a 2. And it turns out that the distribution is going to look, if I did like a histogram, it's going to look something like this. 7, 6, 5, 4, 3. Something like that. So already just starting with something simple like a die, as soon as we have 2 of them, we can start to get something that's a little bit more interesting, a little bit more complicated. So in general, this is what's called a discrete situation. We could look at a continuous situation. And so imagine we have some function. Let's say this is f of x. And maybe it decays linearly down to here, and then it's 0 from here onward. Changes shape a little bit here, and is 0 from here onward. And what we can do is we can calculate the area under the curve. So if f of x is greater than or equal to 0, and area under y equals f of x is 1, then f is a probability density. And then if we wanted to calculate what is the probability we take on a value between a and b, we would just look and see what is the area under the curve from a to b. And so this is one of the reasons why calculus 2 is such an important subject, because there are so many processes that we want to understand, and it comes down to trying to calculate what is the probability that something happens. And we can either do things with discrete or we can do things in the continuous case. And it turns out in the continuous case, we have what's called the fundamental theorem of calculus. And so this is the highlight of the course. So the big result, we don't use the word fundamental lightly. So fundamental theorem of calculus. So let f of x be a nice function. So bounded differentiable is more than enough. And big F, any function such that the derivative of big F equals little f, then the area under y equals f of x from x equals a to x equals b, which we denote by the integral from a to b of f of x dx, is big F of b minus big F of a. So we actually have ways to find areas under the curve if we can find antiderivatives. So the question then becomes, how easy is it to find an antiderivative? In calculus, no matter how hard I try, I cannot take any combination of the standard functions and give you a problem where you can't find the derivative. And the reason is we have all these different rules of differentiation. We have the sum rule, the constant rule, the multiple rule, the chain rule, the product rule, the quotient rule, the power rule. And I can just keep hitting whatever complicated beast I have with one of those. And so no matter what I give you, I can always find a function that's the derivative of the given function. It may be a lot of work. It may be painful. I may not be enjoying it, but I can do it. It turns out most functions don't have an explicit closed form expression for their antiderivative. Most functions, unfortunately, we just can't write down something in closed form. And sometimes when you think we can do something in closed form, we really can't. We've just introduced a name for it. So for instance, sine and cosine. We can only evaluate sine and cosine, exactly at a few key angles. Basically the 30, 45, and 60. And then we can use some trig identities to get some others, but an arbitrary angle, we can't write it down except as an infinite sum. So the question is, if we can't write down the integral, the antiderivative for most functions, how useful is this? Well, fortunately, there are so many functions that we can write down the integral of, and these functions have so many different shapes that we can often do a wonderful job of approximating what's in the real world by looking at these functions. And so even though it's not a perfect match, it's close enough, and we can use that to solve a lot of problems that we care about. So I do a lot of work in baseball mathematics, and later in this semester, I will be talking about an application of calculus that's on the front of all standings pages, Pythagorean expected one-loss formula for teams. And I showed a way to justify why this empirical result seems to work by basically integrating some functions. And I took a phenomenon that was going on in the real world, how many runs are scored in a game, and I modeled it by a continuous function that has a couple of parameters. And by choosing the parameters appropriately, I can get it to do a pretty good job of matching the shape, good enough so that we can make reasonable estimates. And this is another, big idea to get in mathematics, is that you need to figure out what are you trying to solve in the real world. And when you're trying to solve things in the real world, it's often enough just to be close. You don't have to be perfect. Okay, so this is one of the main themes of the class, is to find areas under curves to find antiderivatives. So we want to find antiderivatives because we can use that to find areas. We can use these areas to find probabilities. The other thing that I'm going to just briefly touch on for motivation, and then we'll call it a day, is some applications from physics. So hopefully people have seen some physics like Newton's law of gravity. I want to talk about the idea of passing from a finite sum to an infinite sum, from a finite process to an infinite process. You have to be very careful whenever you deal with infinities in mathematics. Whenever you see an infinity, this is a danger sign that something is going on. And so what you want to do is I want to motivate integration by looking at trying to prove one of the most important integrals in the history of the world. That if you have an object like a sun, and it's attracting an object like a planet, you can assume all of the sun's mass is at its center, and you can assume all of the planet's mass is at its center. And again, this is going to be an extremely difficult integral to do, but it's extremely important. To really do it properly, it's a Calc 3 problem, but there are some tricks we can do to make it almost like a Calc 2 problem. And this was one of the great insights Newton had, because if you have to take into account the force of gravity from every pair of atoms, it's just an overwhelming computation. But if you can say, hey, I can regard the sun as a point and the planet as a point, this is much easier. Now, one caveat is just because something works in one regime does not mean it always works. So you have to be very careful about what are you assuming. It turns out that the formula we derive only works if all of the sun's mass and all of the planet's mass are separate. The planet is not inside the sun. If that happens, you actually get a different law of gravity than what I had mentioned. So I don't want to go into that now. I just want you to be aware of, you have to be careful. So if you haven't seen Newton's law of gravity before, it says between any two objects in the universe, there's a force of attraction. And the force is proportional to the product of the masses, m1, m2, and it's inversely proportional to the square of their distance. So if you double the separation between the planets, the force of gravity is 1/4. If you triple it, it's now 1/9. And if we had to calculate, as I said, the force from every atom of the sun and every atom of the planet, it would just be a calculation well beyond anything we could do, let alone what they could do in the 1600s. And so what we want to do is we want to start off by doing some symmetry arguments. And this is a really good skill to learn, is the phrase without loss of generality. What can I do to simplify the problem to make it a little bit easier to study? Well, so, on the left, I have my sun, and, I have maybe the planet Mars, the red planet. Well, without loss of generality, why don't I choose the coordinate system so that the planet is right above the north pole of the sun? And that just makes writing down the coordinates of things a little bit easier. The laws of physics should not depend on how I orient my coordinate axes. Okay, so we're going to put the planet there. Oops. And now what I'm going to do is I'm going to approximate the sun by a bunch of points. And so, for instance, if the sun was a cube, it would look something like this. What we're going to do is, since the sun is a sphere, what we'll do is we'll take all points, maybe with integer coordinates, inside a sphere. And then maybe what we'll do is we keep changing the spacing between the points. We keep changing that fundamental gap so that we get more and more points inside the sun. And the more points we take, the better approximation we're going to get to the sphere. If we have a very large gap, we're only going to have a couple of points inside, and it's not going to be so good. But as we get more and more points, if the sun has a radius, I know the Earth's radius is on the order of, say, 8,000 miles. If we have a separation between points on the order of 1,000, that's not great. But if we have it on the order of 1 mile, there's going to be so many points that we're going to just miss a small amount on the boundary, and it should hopefully be good. And what we can do is we can calculate what is the force on the planet for finite configuration like this, and then try to take the limit as we take more and more points and see, does that converge to assuming that all of the mass is at the center point? So if the sun has a mass of, say, 1 solar unit, and we have n points, each point would be given a mass of size 1/n. And so as we take more and more points, the mass of each point becomes smaller and smaller and smaller. So does everybody understand the general framework here? We're trying to pass from a finite sum to an infinite sum. This is what calculus is all about. And the hope is that calculus and integration can allow us to add all of these contributions. And so I just wrote some code in Mathematica to just do the calculation. I'm happy to talk to people about how to do coding. And then I have a plot over here. So on the left, we're comparing the gravitational force of an object at height h above the north pole of a unit sphere in 2 ways. The first is all the masses at the center, and the second is we are dividing things up by going plus or minus 40 in every direction. And so when you look at things on the right, you really can't tell the difference. Does it look like there's 2 sets of dots? I'm fortunate, I'm in the classroom, I can look over, and I really can't see the difference. The dots are basically right on top of each other on the left. The calculation of the force from assuming all the masses at the center to doing some approximation looks about the same. And the x-axis is just how far we are. we're calculating several different separations. But whenever you have two things that are really close, you shouldn't plot their values, you should plot their difference. And when we plot the difference, we can see that when they're 2 units apart, the distance is about -6 times 10 to the -6. And by the time they're 10 units apart, it's very hard to see the difference. So the question is, when you see something that differs by 6 times 10 to the -6, anybody know roughly how big is 10 to the 6? So what numbers of size 10 to the 6?
Millions.
It's about 1 million. So I think this is equivalent to, if you take, I think 5 maybe of the Harry Potter books, there's 1 million words. And so 1 in 1 million would be, I circle 1 word and you randomly open the book and you get the same word that I circled. To just try to put things in perspective, what are the odds of like 1 in 1 million? Very unlikely. So the question is, if we were to take a more refined mesh, instead of doing it 40 steps, if we did 400 steps or 4,000 steps, would it converge to 0? And is Newton's conjecture that we can assume all the mass is at the center, is that correct? Or maybe not. Maybe there's something fundamental. Maybe there is a small difference between them. So just a little bit of advanced material. We have Einstein's theory of special relativity, which basically says that speed is not additive. So what does this mean? If you're on a train that's moving at 100 miles an hour and you're walking in the same direction of the train, say you're running at 10 miles an hour, you might think somebody on the ground sees you traveling at 110 miles per hour, the 100 miles from the train plus 10 miles that you're going. It's not quite that. There's a small little division in the denominator. And again, I don't want to go into the details, but you're dividing the product of your speeds, your speed and the train speed, by the square of the speed of light. The speed of light is 186,000 miles per second. We're talking about 100 miles per hour for the train, and that's per hour, 3,600 seconds in an hour. So the difference in the denominator from what it actually is and 1 is so negligible that for hundreds of years when people were doing experiments, it looked like speed was additive to within the level of accuracy that people could measure. And it wasn't until we had much more accurate measurements and objects moving a little bit faster that we were able to see the difference. So you really want to be careful about making assumptions from data and observations. Just because something looks true does not mean it's going to continue. And so just plotting the difference between the Einstein correction and the actual prediction, we actually get errors on the order of 10 to the -6, for speeds of around, for like a rocket ship, you're in the, so many thousands of miles per hour. So the error is actually comparable to what we would get in trying to do calculus. So the whole point of this is just to give you a warning of, we have to be careful. We do need to prove these things. Sometimes these small differences can be indicative that something really interesting is going on. All right, so this is a good place to end class for today. If you have any questions, feel free to shoot me an email. I have to unfortunately log this off now to start having it save and get ready for the next class. So have a good rest of the day. Take care.
Thank you.
Thank you.
Thank you.